Okay, I mentioned linear combinations in passing, but now we're going to formally introduce them. So here's the setup. We're going to start by assuming we've got two things. First thing we have is a list of vectors in Rn. So we'll index those vectors 1 through p and call them v. So that's the first thing. We've got some vectors, v1, v2, all the way up to vp. The other thing we have is we have for each of the vectors in that list, we've got a dedicated scalar assigned to it. So in other words, for the vector v1, we have a scalar c1. For the vector v2, we have a scalar c2, and so on, all the way up to the last vector vp, we have a scalar cp. So now what we're going to do is we'll look at this vector equation. First, look at the right-hand side. You've got each of the vectors is multiplied by its corresponding scalar. So we've got the vector v1 is multiplied by c1, vector v2 is multiplied by c2, and so on, all the way down to vp is multiplied by the vector cp. So you've got a scalar multiplication attached to every single one of those vectors. And then what happens? Then they're all added together. And then it looks like all we're doing is just assigning the result of all those calculations, we're assigning that to the vector y. So y is just a label for everything that's happening on the right-hand side of this equation. So any vector that you can form in that way, so think of it as just y at this point. Any vector like y that you can build in this fashion is called a linear combination. And it's not just like the grammar would say, it's not just a linear combination, it's a linear combination of something. It's a linear combination of the vectors v1, v2, all the way up to vp. And those coefficients, in other words, the scalars that we multiplied onto those vectors, those are referred to as the weights of the linear combination. So formally, we would say that y is a linear combination of the vectors v1 through vp with weights c1 through cp. Okay, let's look at an example. So here we've got a vector y, and notice in this example, we're actually given the coordinates of the vector. So we've got a vector y. It's a two-dimensional vector with coordinates 4 and 7. And then we've got these two other vectors, v1 and v2. They're also two-dimensional vectors. So v1 is the vector 1, 1, and v2 is the vector negative 1, 2. So the question that we're being asked is this vector y, is it a linear combination of v1 and v2? Okay, so well, to answer that question, you'd better be able to come up with the weights. Right? If you can come up with weights c1 and c2 that make y equal to c1 v1 plus c2 v2. Let's start with that. Let's just write that equation down. Let's say y is equal to c1 v1 plus c2 v2. If this is possible, well, then the answer is yes. Then y is a linear combination of v1 and v2. So let's see what this would look like. Maybe this won't work. Maybe it will work. We don't know yet. But let's just use this equation as a guide and see what it leads to. Okay, so what we're going to start by doing is just replace all the vectors y, v1, and v2. Replace them with their actual definitions. So y is the vector 4, 7. And then on the right-hand side, we've got is equal to c1 times v1, which is 1, 1, plus c2, which is the vector negative 1, 2. Okay. By the way, this is a vector equation. Now, that's what this section is supposedly all about, right? Is vector equations. Well, now here's your first real vector equation. It's an equation, and guess what the left and right-hand side are? They're both vectors. Okay, and to emphasize the fact that the right-hand side really is a vector, it looks like it's two vectors that are multiplied by scalars and then added together, which is also true, but it's also one vector. We can do something. I like to use the phrase collapse the right-hand side here. So I'll show you what I mean. The left-hand side we're not going to do anything to. But the right-hand side, I'm going to multiply those scalars into the vectors. I don't know what the scalars are, but I could still follow the rules of vector arithmetic and multiply them in, right? So if I multiply both of the coordinates 1 and 1 by c1, this is what I'm going to get. So this is what it looks like if I take this c1 and multiply it into the vector v1. And then I'll do the same thing with the scalar c2. I'll multiply it into the vector v2. So we'll have negative c2 and 2c2. Okay, and then now there's vector addition on the right-hand side. Again, I don't know what c1 and c2 are, so I don't know what all those entries are, but I do know the rules that I would follow to add them up. So I can still add them up. I'm just going to have c1s and c2s floating around, and that's okay. So on the right-hand side, the first coordinate, I'm going to have C1 plus negative C2, which is just going to be C1 minus C2. And then for the second coordinates, if I add up these, I'll get C1 plus 2C2. So I'll have C1 plus 2C2. And that's what I mean when I say the right-hand side is also a vector. And if I write it as a single vector, then this is what I would get. So you'll hear me say this lots when I say, if I say collapse the right-hand side, usually, I could just as easily have said the left-hand side if that had been appropriate. Usually what I'm referring to is something along in this form where I'm just going to multiply a whole bunch of coefficients into the coordinates of vectors and then add them up or potentially subtract them depending on the context. In this case, we added them. Okay, well, and why did I do this? Well, now we've got an equation involving just two vectors. We've got two vectors, one on each side of the equation. They each have two coordinates. And you may remember a comment I made a little while ago, is that two vectors are equal only when each of their corresponding entries are equal. So the only way that these two vectors could be equal is if C1 minus C2, that would have to be equal to 4, and then C1 plus 2C2 would have to be equal to 7. So actually this led us to a system of equations. And so that's what I mean when I back up and I said we started with this equation where we would let's back it up here. What were we talking about? We were just trying to see is y a linear combination of the v1 and the v2 vectors. So we started by just writing out what would it look like if the answer to this question was yes. And then we just wanted to follow that and see where it led us. Well, it led us to this system of equations. And it looks like if this system of equations has a solution, then the answer to the question is going to be yes. Y is a linear combination of V1 and V2. How will we get the weights? Well, by solving the system, right? Finding the solution to the system. If that system doesn't have a solution, well, then that just means that Y is not. Let me back up. It just means that this is impossible. It means it's impossible to have this equation be satisfied, which means that Y is not a linear combination of V1 and V2. So in order to see which one is true, let's actually solve the system. So let's use an augmented matrix. I got some space up here. I'm going to start over up top. So I'll have the coefficient matrix will be 1, negative 1, 1, and 2. And then the constant column is 4 and 7. And let's row reduce this now. So I'm going to take row 2 and replace it with row 2 minus row 1. And that's going to give me 1, negative 1, and 4 will be the first row won't change, but then we'll have 0, 3, and 3. Okay, and now I can multiply the second row by 1/3. And that'll give me the following. I'll have the first row still won't change, so 1, negative 1, 4 is still our first row. Second row is 0, 1, 1. And then lastly we'll add the second row to the first row. So take row 1 and replace it with row 1 plus row 2. And that'll actually achieve reduced row echelon form. And it'll also show us that this system does have a solution, and we'll be able to see what the solution is. Okay, so what's the solution? The solution is something's wrong here. What did I felt like something was wrong. Okay, so we added row 2 to row 1. That 3 shouldn't be a 3, it should actually be a 5, because 4 plus 1 is 5. Okay, that's what we want. Okay, so we've got C1. The solution is going to be C1 is equal to 5. That's what you get if you write out this equation, and C2 is equal to 1. That's what you get if you wrote out this equation. Okay, so let's go back to the context. This isn't our final answer, right? Because we weren't asked to just solve this linear system. We were asked, is this possible? And it turns out, if we got a solution to our system, the answer is yes. So that means we can say this. We can say, therefore, y is equal to 5v1 plus 1 v2. Right, so that's real. I'm just taking this equation and I'm rewriting it with the C1 and C2 actually plugged in. So but because we can do this, we can say the answer is so yes. Y is a linear combination of V1 and V2. Okay, so that's our big conclusion here. And by the way, you might ask the question, well, once you know there's a solution, like let's say you get up to this point, and you've solved enough linear systems to know, and you can recognize once you get to this step, you can say, okay, I can't necessarily solve this in my head, but I can see at this point that there's going to be a solution. Can I just stop now and say the answer is yes? Technically, you could, but when you're asked, if you're asked a question, if you're asked, is one vector a linear combination of some other vectors, you want to find out what the weights are, right? And you're not going to know what the weights are unless you actually solve the system. So the weights are C1 is equal to 5 and C2 is equal to 1. Without actually solving the system, you're not going to know what those weights are. So the proper way to answer a question like this is to go all the way to the point where you get an actual concrete solution so that you can actually write the vector y as a linear combination of v1 and v2. Okay, a couple of observations that we can make here. Let's go back up to this augmented matrix. Let's look at the first column. And then let's look at the second column. You'll notice that the columns of the coefficient matrix here are actually the vectors v1 and v2. And moreover, the constant column, which is really just the constants 4 and 7, that was the vector y. Okay, and that wasn't a coincidence. That's what's going to happen. When you write down a vector equation like this, this is exactly what's going to happen every time. So some of these steps here, you can save yourself the trouble and not go through all the details. Now, it's best to just do. Doesn't take so long to actually write them out, and then you'll be certain every time. So I encourage you to actually write out the details. But let's mention this, or let's go through this observation below. The point is, once you observe what happens every time, you can take some shortcuts here and shave off a few of these steps. But let's state the observation first before we make a decision on what can be skipped. Okay, so let's start over now. Completely forget about that example now. Let's go back to the general situation. So our setup is this: we've got some vectors. We've got a bunch of a's. A1, A2, all the way up to AN. And then we've also got this extra vector B. And the idea is that those vectors are all in Rm. So N is the number of vectors in your list of A vectors, and then M is the number of coordinates that each of those vectors has. And then you've got a sequence of scalars as well. You've got a scalar attached to each of the A vectors. Here, just basically, that's all the setup that's required to be able to build this equation. Okay, so we've got the idea is we've written B as a linear combination of the vectors A1, A2, all the way up to AN. Okay, so that's the most general linear combination you could write down. Okay, maybe it's true, maybe it's not, right? Depends on what the vectors B, A1, A2 up to AN are. Depending on what those vectors are, and also depending on what the scalars C1, C2 up to Cn are, this equation may be true or it may be false. But regardless of whether it's true or false, the equation is going to be equivalent to this system. Okay, so what is this? It looks like it's an augmented matrix, but it's only got one row, right? But be careful. This is not a number. This is not a real number. A1 is a vector, not a real number. Same with A2. That's not a number, that's a vector. And same with B. B is not a number, it's a vector. So it looks like we've got an augmented matrix, but and it's a single row augmented matrix, but instead of real numbers as entries, we've got vectors. So the way you should interpret that is think of them as columns that are just collapsed down for brevity. So for example, in our notation up here, imagine if we put brackets like this and essentially just said, okay, this augmented matrix that I am pointing to with the arrow, it's abbreviated by this notation here. That's what's going on down here. This is the abbreviation of a linear system. Or pardon me, this is the abbreviation of an augmented matrix. And the idea is that's an augmented matrix that's going to be equivalent to a linear system, which is equivalent to this vector equation. Just like in our example, we had a vector equation, which was equivalent to a linear system, and that linear system was equivalent to an augmented matrix. So that's the observation says what's going to happen in general, but if you refer it to this example, you can see what it looks like in a specific case. Okay, so if you're answering a question like this, you're allowed to just say, okay, I got this equation, and jump right to this augmented matrix. But I just want to give you a word of caution: be very careful. I don't think it's this is not something that you want to sit and memorize and repeat to yourself over and over again and just memorize it blindly without understanding why it's true. My suggestion is just write out these details until you've done them so many times that you can do them in your sleep, and you can just, and you'll just eventually just do it in your head. And then you can, and then when that happens, you can jump right from this line to this line, and you'll do it with confidence, right? You won't be doing it with uncertainty.